All right, let's take a look at problem 2.1, number 21 here. Similar to a lot of the work we did in problem number 9 here, where they give you a graph and they want you to do some interpretation from that. So 21 says the number p of t, so that of course is your independent variable, it's your function, your y value here, the number of E. coli cells at a time t in hours, so t is your independent variable, your x, in a Petri dish is plotted in figure 11 here. So A, calculate the average rate of change. Let me stop reading for just a second. As soon as they use the word average, we know what it is that we have to do. This is slope of a secant, and it's going to require 2 data points. And sure enough, they give you that. So calculate that average rate of change of this function over the time interval from 1 to 3. So I'm looking at the blue curve here, and at the time t equals 1, we get this nice clean point right over here, which looks like the ordered pair of 1, and then a value here of 2,000. All right, and that's how many E. coli cells we have in the Petri dish at 1 hour. And then at 3, we're right over here, and that is another relatively clean point. That looks like the ordered pair 3. And at that point, it looks like we have 8,000 E. coli cells in our Petri dish. What I'm hoping you guys remember from the last 2 years in math, if not from your biology classes, is that when we talk about growth of an organism, very often like a bacteria or a virus or something like that, it tends to follow a pattern of exponential growth, increasing at an increasing rate, where the percentage of growth from one time unit to the next remains constant. And that's what it kind of looks like is happening right here. So we're supposed to come up with an average rate of change here, so we know how to do that. Average rate of change is equal to, now we would normally write delta y or delta f, over delta x. Here I guess what we're doing would be delta p, because that's what we're actually measuring over a change in time. So here we go. Ending y value right here, 8,000 was our ending population, minus your starting y value, which is going to be 2,000. All over your change in x, or in this case your change in time. We're ending at 3 hours, and we're beginning at 1 hour. However it is we're defining our time here. So our change in population then, it grew by 6,000, and the change in time right there from 3 hours to 1 hour is 2, and I don't even think we need a calculator for this. We ended up with 3,000. Our units right there would be the number of cells we're talking about. That's what it said we were measuring here, and our time unit was going to be in hours. So our E. coli population is growing at an average rate here of 3,000 cells per hour, but you got to finish this sentence now, guys, on the interval from 1 to 3 hours. That number would be different if we changed the interval here. So, okay. And the last thing it said to do for part A was to draw the corresponding secant line, which for no good reason I usually do in green. And our secant line then is the one and only line that is defined by the 2 points that they gave us. So there's our secant line in green from t equals 1 to t equals 3. Now, part B is asking us to shift gears a little bit here. B says, estimate the slope m of the line in figure 11. So they're talking about the red line that we have here, and what does m represent? Okay, so 2 different questions right here. So for m, we've got to come up with the slope of that red line, and kind of like we did back in problem number 9, you need 2 points on a line if you're going to determine its slope. So as fun as a lot of that was, I think I'm going to erase and try to simplify this diagram here a little bit, guys, and say, okay, if this is where we're at right now, that red line needs 2 clean data points on it. And I feel pretty good still about this point right here for the red line. So I think I can still, I guess I didn't need to erase the point 1, 2,000. That works on my red line as well. But as far as my next clean point, I don't think I see another one until maybe right about there, which kind of looks like it would have a t value of 4, and boy, to me that y value, that p value, looks just a hair under 6,000, but you know what? If they wanted us to know for sure, they would have given us a table with the values. So I'm going to go with 6,000 and run with that. We need the slope of that red line, so here we go. Change in y, ending value would be 6,000, ending y value I should say, minus the starting y value of 2,000. Gotcha. And then for change in x, or in this case change in t, we ended it at a t value of 4, minus we started at a t value of 1. 6,000 minus 2,000 is going to give us a change of 4,000 units right here of E. coli cells. And down on the bottom, that's over 3 hours. Now that one works out kind of ugly. That's not an integer like the last one here was. So if you guys wanted to leave that answer as 4,000 over 3, I'd be perfectly fine with that. How does that divide out? What is it, guys? It's what, 1333 and a third. You know what? I don't want to create bad habits for you guys. Leave it as an improper fraction. And our units there again would be cells per hour, sorry. So that's what we came up with right here. And actually, the reason I talked about the units here, I got ahead of myself. They said estimate the slope of that line. That's your slope right there, 4,000 over 3. But what does M represent? That kind of tells you right there. What we're doing right there, guys, is we're coming up with, and I hope you realize this, in green, we drew a secant line, a line defined by 2 points on a curve. But that red line, which they drew for us already, is defined just by this 1 point here on a curve. So that red line is actually a tangent. So what we just found right here is the slope of our tangent line. And that tells us, everybody, an estimate here for the instantaneous rate of change of this function here, P of t, evaluated at one specific time value. And that one specific time value is where that point of tangency is located at t equals 1 hour. So in part A, what we were really finding up here, guys, is saying that on the interval from 1 hour to 3 hours, our average rate of growth was 3,000 cells per hour. In part B, we're saying something different. At the single moment in time when t is equal to 1 hour, we feel that at that moment, our population was growing at a rate of 4,000 over 3, 1333.3 repeating cells per hour. The first one was an average rate of change over an interval. The second one we came up with was an instantaneous rate of change measured at just one specific value of time. So that's the big difference between an average rate of change and an instantaneous rate of change. One is slope of a secant, the other is slope of a tangent. One tells us on average how quickly something is growing over a period of time, but the instantaneous rate of change tells us an estimate for how quickly something is changing at one particular instant.